Welcome back. In this video, we're going to talk about finite life estimation, meaning specifically, up till now we've been saying, is this thing going to have infinite fatigue life, or is it going to last at least 10 to the 6 cycles? And if so, we say that the fatigue factor of safety is 1. And if it can last more than that, it'll have some greater fatigue factor of safety. But we don't really have a way of estimating how many cycles it will last, up above beyond 10 to the 6. However, we do see a particular failure relationship of when things fail, when the stress is high enough in the finite life. So finite life happens less than 10 to the 6 cycles. And the way we approach this is by looking at that SN diagram. So recall we have the stress that we put our product under, or our object under, and N being the cycles that it can last. If it doesn't last any cycles and it breaks the first time, we'll call that the ultimate strength. And at some point, say down here, 10 to the 6 cycles, it basically continues on. So the graph looks something like this, and then levels out. So 10 to the 6 cycles gets us this quasi special point, which we call the hypothetical endurance strength. If this is an actual part that we're testing, it's the actual endurance strength. But up until and before this time, there is a linear relationship on this log graph that we are interested in computing. Because if we know that we are at some stress value, then we can say that it should get us some n number of cycles out of this if we are at this level of fatigue strength. So this line, recall, is the fatigue strength of the part, and the fatigue strength is a function of the number of cycles that we want this thing to last. So we have a line fit for this log curve, and this line fit basically looks like this, that the fatigue strength, SF, is A times n the number of cycles raised to the B. So A is a factor where we have F, and which I'll define in a moment, times the ultimate strength squared divided by that endurance strength for our part, and B is -1/3. This is where the log value comes in, finding out what the exponent is of this value again, F times the ultimate strength divided by the endurance strength. And the only thing that's not defined here is F. This F is a ratio between the ultimate strength and the fatigue strength at 10 to the 3rd cycle. So it's basically the point at which this line hits 10 to the 3rd cycle. So trying to come up with a line curve somewhere in the middle there. So sometimes 10 to the 3rd cycles, this, if we do experimental data, it might be around about there. And the 10 to the 3rd point sort of averages it out. That's why it's chosen. So to find F, we look at tables. So specifically, we've got a table in the Shigley book that has it for steels. It can be calculated as well if need be. But for the most part, we'll stick to steel and just use it as a graph. So it tends to fluctuate between about 0.7 to 0.9, depending on the ultimate strength of the material that we're talking about. Great. So if this is the equation of that line right here, between 0 and 10 to the 6 cycles, we can rotate that around and come up with the other useful form of this equation. The other useful form of this equation is N, the life and cycles that we can expect to get from a part, is equal to the fully reverse stress that we put it under divided by A raised to the 1 over B. This is just flipping that equation around. Now note that this sigma rev here, this is the fully reversed stress. In future videos, we'll talk about combined loading. So this is, if you use this equation, you need to first determine what is the equivalent fully reversed stress. But for now, in the simple fully reversed cases that we're looking at, this will just be the stress values that we're at. And when we do this, you're going to come up with some number that looks like it's going to last 106,000 cycles, 582.134, right? So if you take a log number and of this b here and raise it to the fractional decimal point like that, you'll get that many cycles. As an engineer, you must never ever report anything accurately that you're not actually accurate about and that you don't know. So our best accuracy here is going to be, say, something like 100, and even underestimate would be fine, 106,000 cycles. You're close enough. You don't want to be pushing it to get that 700 more cycles out of your part before you say repair it. So try to be conservative on your estimate here. Accurate but conservative. So say we have an example here of a polished part made of 1050 hot rolled steel under fully reversed 55 kpsi stress. This is fully reversed. How many cycles should we expect this thing to last in general without knowing any of the other Marin factors? Well, we know the hypothetical endurance strength is going to be about 50% of the ultimate strength. So we need to know the ultimate strength. This is just a material property which we can look up. And the ultimate strength of this steel that I mentioned, according to the back of the book, is 90 kpsi. So our hypothetical endurance strength would be about 45 kpsi. All right, so I haven't given you any other information. We don't know anything other than just hypothetically how much would the 1050 last. Obviously, with a particular loading situation or particular geometry, we would modify that hypothetical endurance strength a little bit more. But since we don't know it, we can just use it as is. So we can look at figure 618 to find F. So our goal here is how many cycles is this thing going to last? So we want this formulation where N equals the stress we put the thing under over A raised to the 1 over B, with our A's and B's equal to what they were before. And in order to do that, we need to know F, A, and B. So F came from a table, specifically in the Shigley book, I believe it's 618. So that table looks like this graph, and is a relation to the ultimate strength to the F ratio. So we were at an ultimate strength of 90 kpsi, so that puts us fairly close to 0.86. We could probably round up just a little bit there. So this is very close to 0.86. So recall our A value from above and our B values. Our A was calculated as F times the ultimate strength squared over the endurance strength. In this case, it's going to be our hypothetical endurance strength since we don't have anything else to modify it by. And B is negative 1/3 the log of F times the ultimate strength over the endurance strength. So for our situation, that looks like 0.86. So 0.86, which is just a fraction, times the ultimate strength of 90 kpsi divided by the endurance strength SE, which we found as 45 kpsi. This value is squared. Notice this is kpsi squared over kpsi, so we should just get a kpsi value out of this. So the answer to this would be 133.1 kpsi. So it'll retain whatever units you keep stress and your endurance strength under. Now for B, we have negative 1/3, the log of 0.86 times 90 all over 45. Or in this situation, negative, this will almost always be negative, 0.0785. So a pretty small fraction. All right, so our strength equation, if we were to do the SN diagram, between 0 and 10 to the 6 would look something like 133.1 kpsi times n, the number of cycles that we want this thing to last, raised to the negative 0.785. That's not exactly the form that's easiest for us to use, because our actual question was what was the cycles that we want to get out of this thing. So instead, we'll put it as the cycles that we expect to get out of this part is the stress we put it under, 55 fully reversed bending, or fully reversed stress, divided by 133.1. So this is kpsi over kpsi. So the units that we get out of this should be unitless, which is cycles. It's just a number, an integer. That's not an integer, but it's just a number. Divided by 1 over negative 0.0785. So the answer that you get out of this is 77,500 and something cycles. So I would go ahead and report that as 77.5 times 10 to the third cycles. That is the number of cycles we should expect to get hypothetically out of 1050 hot rolled steel under 55 kpsi of normal stress. So that's generally how you calculate the finite life for a part. So the process goes, for our fatigue analysis, we do what is the stress. So this is from mechanics and materials. From the stress values, we figure out what is the mean and amplitude. From the mean and amplitude stress that we can then apply our failure theory, our fatigue failure theory to be exact. And then if n is less than 1, this is n, the fatigue factor of safety, is less than 1, then step 4 here is to calculate how many cycles we expect the part to get under the loading that we have. Because it's certainly possible that it doesn't last 1,000,000 cycles, but it lasts several 100,000, and we are okay with that. And then finally, we're always going to check to make sure that the part does not yield. And we'll talk about that a little bit more when we discuss the failure theories and how they are defined when we add combined stresses in the next video. That about does it for this video. Until next time.